Hello everybody, it's Tarun. Welcome to your 12th tutorial in the Signal System and Control course. In the last tutorial, I taught you the Fourier transform for periodic signals and general properties of the continuous time Fourier transform. Okay, now we will see one of the two most important properties of Fourier transform, which is the convolution property. Okay, so we are a LTI system having xt as its input and yt as its output. Okay, so recall that e to the power j omega t is eigenfunction whose eigenvalue is h of j omega, okay, which is the frequency response. And you can see that the Fourier series coefficients of output signal are product of Fourier series coefficient of input signal and system's frequency response. Okay, so the Fourier coefficient of yk will be Fourier coefficient of yt will be Fourier coefficient of xt multiplied with h of j omega. So what it will be for aperiodic signals and LTI system? Okay, instead of Fourier series, here it will be Fourier transform. Okay, the Fourier transform output signal will be product of Fourier transform of input signal and its system's frequency response. So now let's see the derivation of this phenomenon. We are deriving it from Fourier series. Okay, for this we are interpreting our periodic signal as aperiodic signal as periodic signal with infinite period. Okay, so this was the inverse Fourier transform formula. To make it if x of j omega is aperiodic, to make it periodic, I have taken time period as tends to infinity, which implies that omega naught will be tending to 0. So I can rewrite this equation to make it periodic in this manner. Okay, so the LTI system with impulse response h of t and its frequency response h of j omega will be Fourier transform of h of t. So if this is the input of a LTI system, then the output we'll get is the similar, but it will just be multiplied with the frequency response. Okay, as you can see here that it is just multiplied with the frequency response only. Okay, so if I make the limit of time period to infinity or omega naught to 0, then I can rewrite this equation in this manner, where I have replaced k omega naught with omega. Okay, so here you can see that it is the Fourier inverse of x of j omega into h of j omega, or you can see that y of j omega will be x of j omega into h of j omega. Okay, or you can directly derive it with the convolution integral, where xt is our input and yt will be minus infinite to infinite integral x of tau h of t minus tau d tau. Okay, so if I take the Fourier transform of the output, then it will be double integral, okay, multiplied with e to the power minus j omega t dt. Okay, so I can rewrite it in this manner. Okay, and it will be h of j omega and integral minus infinite to infinite x of tau e to the power minus j omega tau d tau, which will be x of j omega. Okay, so here you can see that y of j omega will be h of j omega into x of j omega. So the convolution property states that y of t is x of h of, if y of t is convolution of h of t and x of t, then its Fourier transform y of j omega will be h of j omega into x of j omega. Okay, there are some important points to memorize for this property. That convolution in time domain means that multiplication in frequency domain. Okay, and frequency response h of j omega is Fourier transform of impulse response ht. Okay, and impulse response and frequency response both characterize LTI system. So now let's see properties of LTI system in terms of their frequency response. Okay, as similar to the properties which I told you in the unit 1. Okay, now first see the cascading of systems. If I am passing x of t with h1 of j omega, then through h2 of j omega, and I getting the output yt, then xt will be equivalent to, then the yt will be equivalent to the system when xt is passed through multiplication of h1 and h2, or it is also equivalent to the system when xt is passed through h2 first, then h1. Okay, so these all three systems are equivalent. Okay, so and existence of frequency response brings out the convergence property also. Okay, LTI system is Bibo stable, we know that, so it fulfills the first Dirichlet condition. Okay, and practically systems which is something to just memorize, that they also fulfill the Dirichlet second and third condition. Okay, so now let's see some examples related to this. We are having an LTI system with impulse response ht, where ht is equals to delta t minus t naught. Okay, it is a shifted unit impulse, and it's if the impulse response is this, so what will be the frequency response? It will be h of j omega, which will be e to the power minus j omega t naught. So you know that input output relation in frequency domain, which is y of j omega is equal to h of j omega into x of j omega. Okay, so if y of j omega will be e to the power minus j omega t naught x of j omega, and by the time shifting property of Fourier transform, you can see that y of t will be x of t minus t naught. Okay, so now let's see the second example, which is differentiator. I am having we are having yt is equal to dx by dt. Okay, from the differentiation property of Fourier transform, y of j omega will be j omega into x of j omega. So what will be the frequency response of this differentiator circuit? It will be y of j omega upon x of j omega, which will be j omega. Okay, now let's see the third example, which is frequency response of an ideal low pass filter. Okay, I am having frequency response h of j omega is rectangular omega upon 2 omega c, where this function is 1 for mod omega less than omega c and 0 for mod omega greater than omega c. Okay, so its impulse response I can find out with the help of inverse Fourier transform. Okay, and here you can observe that the impulse response is not causal. Okay, and is of infinite duration. So this ideal low pass filter is not realizable, or it is not perfectly ideal. Okay, so this is something, a block diagram you can see for the Fourier transform or the frequency response thing of an LTI system. Okay, if you pass xt through ht by convoluting it, then you will get yt. If you take the Fourier transform of xt, then x of j omega when passed through h of j omega with multiplication, then you will get y of j omega, and its Fourier inverse will give you the output yt. Okay, so now let's see some more examples. First example is where h of t is e to the power minus at ut, and our input is e to the power xt is e to the power minus bt ut, where a is greater than 0 and b is greater than 0. So there are two ways to find out the impulse, the output of this system yt. Okay, one of them is directly convoluting the ht and xt functions, and the second way is transforming them with the help of Fourier transform in frequency domain, then multiplying them and then taking the inverse back, which I think might be easier in this case. Okay, so we have seen the Fourier transform of this type of function will be this and this respectively. Okay, so y of j omega will be the multiplication of both, and now let's see the inverse Fourier transform for this. Okay, first we are considering the case when a is not equals to b. Okay, I can rewrite this equation like this with the help of partial fractions, and now I can find out the value of a and b. Okay, to find out value of a and b, there is one simple method, which is if I am trying to find out the constant of this denominator, okay, then what should I do? I need to multiply this denominator, okay, with this equation, okay, and put the value of omega j omega as minus a. Okay, here you can see that I have multiplied a plus j omega with y of j omega, and I have put the value of j omega is equal to minus a. So I will get capital A equals to 1 upon b minus a. Similarly, I can get capital B equals to minus 1 upon b minus a. So here you can get y of j omega will be 1 upon b minus a upon 1 into 1 upon a plus j omega minus 1 upon b plus j omega. And this is e to the power minus at and e to the power minus bt ut's Fourier transform. So if I take inverse Fourier transform, I will easily get this. So now let's see the second case, which is a equals to b. For a equals to b, our y of j omega will be like this, okay, and it is the inverse, it is the Fourier transform of t e to the power minus at ut, okay. So we are now the next example is ideal low pass filter with impulse response. Okay, here h of t is sinc function and x of t is also sinc function, okay, represented by this term and this term respectively. Okay, so now let's see the output yt. Okay, time and domain approach is again the convolution thing, which can be very difficult to solve. Okay, in this case it will be very difficult to solve. Okay, so we will be following the frequency domain approach only. Okay, as you know that in the frequency domain approach, y of j omega will be h of j omega into x of j omega, and as you all know that the Fourier transform of the sinc function is a rectangular function. Okay, so you can find out the Fourier transform of h and x respectively, and you will get these. Okay, so y of j omega will be this function, okay, a rectangular function only, and where omega naught will be minimum of omega c and omega I. Okay, and again you know that the inverse Fourier transform of rectangular function will be sinc function. Okay, so this was all about the convolution property. In the next tutorial I will teach you about the multiplication property and the frequency differential equations. Okay, linear constant coefficient differential equation. So thank you guys for watching. I will see you in the next tutorial.